In this video, we shall discuss hydrogen spectrum. We know that from our previous video, if you have a hydrogen atom represented by a schematic diagram like this, with a bunch of orbits, and this is the proton, the energy of an electron occupying, let's say, the nth orbit is given by the following equation. It's minus 2.18 times 10 to the power minus 18 over n squared in joules, or in electron volt it is just minus 13.6 over n squared. So in this video we will show how to use these results to determine the hydrogen spectrum. So let's go back to this schematic diagram. Let's assume initially an electron is here. So that is the initial orbit, or it is an nth orbit. Then let's assume it makes transition to that orbit. So that is the final orbit. And let's call it is the nth orbit. In this process, energy will be radiated. And this radiation would have certain wavelength and frequency. The energy radiated equals the energy in the initial state minus the energy in the final state. Substituting this expression in here, we get energy initial is minus 2.18 times 10 to the power minus 18 over Ni squared minus EF. So EF is minus 2.18 times 10 to the power minus 18 over NF squared, which can be rewritten in the following manner. 2.18 times 10 to the power minus 18 times 1 over NF squared minus 1 over Ni squared. So that is the amount of energy radiated in joules. We mentioned a few minutes ago that this radiation would have its own wavelength and frequency. Let's denote the frequency with the letter nu. And the energy radiated delta E is given by the Planck constant times the frequency of the radiation. So substituting this result for that, and also realizing that frequency times a wavelength is the speed of that radiation, in this case the speed of wave of light, delta E simply becomes h c over wavelength equals 2.18 times 10 to the power minus 18 times all that. H is the Planck's constant. The value is 6.626 times 10 to the power minus 34 joule second. C is speed of light in vacuum. It's 3 times 10 to the power 8 meter per second. Substituting these two numbers in here, we get the following expression for 1 over a wavelength. Namely, it is 1.097 times 10 to the power 7 times 1 over NF squared minus 1 over Ni squared. This constant here is called the Rydberg constant. And the unit is 1 over meter. And this is the result that we use to determine the hydrogen spectrum. So let's do just that. What we have here is a schematic diagram of hydrogen atom with various orbits represented by orbital number, n equals to 1 all the way until n equals to 6. Now let's assume the electron of this hydrogen atom is initially at n equals to 6 orbit, like that. And it makes transition to n equals to 2 orbit, like that. The wavelength of the radiation emitted can be calculated using the equation that we have just discussed a few minutes ago. 1.097 times 10 to the power 7 times 1 over NF squared. So this is the final state. So NF is 2, so 1 over 2 squared. And the initial state is n equals to 6 state, so 1 over 6 squared. And solving for the wavelength, you get a wavelength of about 4.1 times 10 to the power minus 7 meter, or about 410 nanometer. So the radiation emitted would have a wavelength equivalent to that number. If the transition of the electron occurs from n equals to 5 to n equals to 2, like that, the wavelength of the emitted radiation can be calculated using the following result. So 1 over 2 squared minus 1 over 5 squared. That will give you a wavelength of about 434 nanometer. Namely, the radiation emitted for that transition would have a wavelength of that number. Likewise, a radiation that is the result of transition from, let's say, n equals to 4 to n equals to 2 would emit light or radiation with some other wavelength. And finally, let's say from n equals to 3 to n equals to 2 would emit radiation with a wavelength of about 656 nanometers, and so on and so forth. So all the transitions that begin with a higher orbit and end up in n equals to 2 orbit give rise to radiations that belong to the so-called Balmer series. Other series are also available. For example, for transition from higher up orbits to, let's say, n equals to 1 orbit would result in transitions like that, and the formula that describes the wavelength of these radiations are given by this expression. Note that the first term in the denominator is 1 instead of the previous 2, because all the transitions here terminate at n equals to 1. This is what we call the Lyman series. If the transition terminates at n equals to 3, then the equation for the wavelength will look like that, and the series is known as Paschen series. For transitions that terminate at n equals to 4, the resulting wavelengths belong to the so-called bracket series. And finally, for transitions that terminate at n equals to 5 orbit, the wavelengths belong to the series known as the Pfund series. One such example is the transition from n equals to 6 to n equals to 5. Now let's look at the problem. In the Balmer series, find the longest wavelength radiation emitted. Determine also its frequency and energy. So the Balmer series is represented by this following equation. Note, this R is the Rydberg constant, whose value we know, times 1 over 2 squared minus 1 over n squared. You want the longest wavelength radiation, so that means this is maximum. So 1 over lambda has got to be minimum. So that happens when n here is 3. Substituting that, you get R 1 over 4 minus 1 over 9. And the longest wavelength will turn out to be 6.56 times 10 to the power minus 7 meter, or quite simply 656 nanometer. So that is the longest wavelength in Balmer series. The frequency can be determined by taking the speed of light. Note that this radiation is electromagnetic radiation. So electromagnetic radiation with this much wavelength is actually a visible light on the red end of the spectrum. So C indeed refers to speed of light in vacuum. That divided by the wavelength of the longest wavelength that we have just calculated. Speed of light is 3 times 10 to the power 8 meter per second. The wavelength that we have just calculated in meters is 6.56 times 10 to the power minus 7. The answer will be in a unit of hertz, and that's going to give you 4.57 times 10 to the power 14 hertz. And finally, the energy of the radiation. That is given by the Planck's constant times the frequency that we have just calculated. Planck's constant is 6.626 times 10 to the power minus 34, and that times with the frequency of that much, which is 4.57 times 10 to the power 14 hertz, will give you the energy in joules, and it will turn out to be 3.03 times 10 to the power minus 19 joules, or in the unit of electron volts, it's about 1.89 electron volts. Part 2. Find the shortest wavelength radiation emitted in the Balmer series. So again, if lambda were to be the smallest, 1 over lambda has got to be the maximum. For that to happen, this has got to be infinity, so that 1 over infinity approaches 0. So the shortest wavelength is given by that equation. So Rydberg constant is 1.097 times 10 to the power 7 divided by 4 is 1 over lambda short. So the shortest lambda is 3.65 times 10 to the power minus 7 meter, or in nanometers it's 365 nanometers. And that solves the problem. Thank you for watching.